Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, good afternoon, everyone. We're happy to have Jordan Greenblatt update us on the latest in this topic of maximal inequalities on Cartesian products, a topic which was essentially started here a few years back when Alexandra Kolla was a postdoc. So anyway, we're happy to hear Jordan.
Thank you. Thank you for the invite, and thanks everyone for coming. So the topic is sort of a funny split of classic harmonic analysis and graph theory. So since I assume most people here have a better graph theory background, I want to explain some of the harmonic analysis sort of classical context for this and lead it in just to give some motivation. So one of the most important objects in all of harmonic analysis is the Hardy-Littlewood maximal operator. And this will be the Euclidean one on RD. And there are going to be some minor technical assumptions on F, but since we're not really talking about Euclidean space, I'm just going to completely brush those over. So this is defined as the maximal average over all spheres centered at the point x of the function f. Incidentally, all our functions are going to be non-negative, but I'll try to remember to put in absolute values. If I don't, just assume they're in as far in as they can be. There are some silly conventions, but it doesn't matter. For all we care, they can all be non-negative. And I'm going to use m for maximal functions throughout. If it's ambiguous because there's more than one in one section, I'll just use subscripts or something like that. OK. So yeah, this is the maximal average or supremal average over all balls centered at a point. For an example, in dimension 1, we have the indicator of an interval. So f looks like, it's just a step. And then mf, the maximal function, looks a bit different. So in the interior here, it's going to equal 1, because you can just take a radius small enough that the entire ball is contained in the interval. So you get this. And on the boundary, it's a half. It's pretty easy to check. And then it decays linearly. So by this, I mean it's bounded above and below by constant multiples of 1 over x. What did you say?
Inverse linear.
Inverse linear, sorry. I would have said grows, otherwise I didn't want a double negative. OK, so it grows inverse linearly. OK, I'm done. I'll get back to the actual talk. So 2 things to notice here. One is that it's an L-infinity contraction. So if f is bounded, right, no matter what f is, if f is bounded, then all of its averages share the same bound, and so the maximal function also does. However, not only is it not an L1 contraction, it's not even bounded in L1. Right? This is a nice integrable function. It has total mass 2, but this one has poor decay or inverse growth. And as a result, it just goes too slowly off to infinity to be integrable. And so a natural question is, what about for p in between? And this is the first classical theorem we're going to talk about. This is the Hardy-Littlewood maximal theorem, which says that for all p greater than 1, this is actually a specific part of it, but it's the part that's relevant to us. For all p greater than 1, the maximal function is bounded up to a constant in LP by f. This dependence on p is inevitable as that picture would suggest. As p goes down to 1, the bounds are going to go to infinity. I'll get back to this dimensional dependence in just a moment. This was later strengthened by Stein, I think rather remarkably, to the spherical maximal operator, which is exactly what you'd expect. Here we're looking at spheres centered at x, surface of spheres, rather than interiors of balls. Keep in mind, by the way, that this operator pointwise dominates the Hardy-Littlewood maximal operator, simply because an average over a ball is just a weighted average of averages over spheres. So this is a much more dangerous operator, I guess, for lack of a better way to say it. What he showed is for all d greater than or equal to 3, this was later extended to 2 by Bourgain, p greater than d over d minus 1, test on deltas to see why that's necessary, we have an LP bound. Again, and the constant will be dependent on p. Originally, the dependence was very bad. Oh, sorry, no, the dependence is very bad. Right, so there's bad dependence on p, but remarkably, as long as p is greater than this threshold, we do have this bound, and also the constants in the inequality can be taken to be non-increasing in d. Once the dimension is high enough for a given p that it crosses this threshold, these constants are non-increasing simply because you can view the averaging process over a sphere in dimension d plus 1 as two random processes, picking a random direction in the sphere of dimension d plus 1, and then averaging over the cross-section, picking a random element of the cross-section. And those two combined, it inherits the bound. It's actually a very elegant method called the method of rotations. This says thus Stein. He's an important guy, but still seems weird. And so in particular, this lets us get rid of this dimensional dependence. The original dimensional dependence from the classic proof is actually exponential. It's a nice proof, but it's ugly dimensional dependence. But here, for a fixed p greater than 1, up until d crosses this threshold and cuts under p, we can just use the classical constants. It's finitely many cases, and then we can just use the constant that comes for all dimensions higher for the spherical, since it dominates the ball. And this is the sort of thing we're going to be talking about today: dimensional constants for spheres in the setting of finite graphs rather than Euclidean space. But before I step forward, I want to say, since I imagine this is new to some people, that it's not just contrived. There are applications. In fact, this is, like I said, one of the most important tools in analysis. One reason is for pointwise convergence questions. So the first thing I learned, and I think a lot of people learn as a corollary, which you've all pointed out was not the original proof, but implicit in the original proof, and is in the actual original proofs of a lot of other pointwise convergence questions, is the Lebesgue differentiation theorem, which says that if we average the function f over a ball centered at x and send the radius to 0, then this limit exists and is equal to f of x for almost every x, or if you like, almost surely over any reasonable probability on Euclidean space. And this is sort of remarkable. If f is continuous, this is the fundamental theorem of calculus. If f is hideously jagged, that's not at all obvious, I think, for almost every x. Sorry. And this uniform control that comes from the maximal bound is what gives us this. Now, in a discrete setting, pointwise convergence is less meaningful, but what's not is probabilistic bounds. So here's where I'll introduce our first non-classical theorem, which is the work of Harrow, Kolla, and Schulman that you've all alluded to earlier. And this is on the hypercube, which we're going to write as k2 to the n because we're generally doing it for cliques, but we'll use this funny notation. On k2 to the n, we define pk to be the spherical averaging operator, expectation of a function over the sphere around x. Here k has to be an integer from 0 to n because that's the diameter of the hypercube. And our spherical maximal operator is, again, what you would expect. It's the maximum over k of what they proved is that there is a dimension-free L2 bound. In other words, I mean, for a fixed hypercube, it's a finite dimensional space. It's not particularly interesting. But asymptotically, there's no dependence on this dimension n, which is a rather remarkable and non-trivial phenomenon. And the way this came up, just to give some motivation, was in the context of Alexandra looking at the UGC, the Unique Games Conjecture, rather, here at Microsoft, right? And so without going into the full details of the original problem, I'll give some intuition for how it came up and how this sort of thing might come up naturally. And the image she had was, imagine you have a hypercube and there's some information spread out around the vertices. And the way you can find out information is by starting at any seed point on the hypercube and work outward. So you pull all of the neighbors of your seed point and get the information there. And if you get good information, you can use that to examine the sphere of radius 2, which you can use to examine the sphere of radius 3, and so on. Now imagine there's an adversary who wants to obscure this information, and they have a limitation on the amount of bad information. Take these terms with a grain of salt. I'm trying not to be too quantitative in the interest of saving time. But you as the player have control over how much bad information they can spread, thinking of it in terms of mass, sort of vaguely. And what they want to do is spread bad information. So here I'll use these chunks to represent bad information. They want to represent he wants to spread bad information in such a way that eventually, starting at a given seed point, when you survey a sphere, you get a large portion of misinformation, and then it ruins the process for the rest of your search of the graph radially outward. And so, imagine we started at this seed point. Here, there's a little bad information, but it's not enough to throw us off our track. Here, on this second one, there's a little more, but maybe it still doesn't hit that threshold. But here, on the sphere of radius 3, we see a ton of bad information. And there's so much that when we look to the sphere of radius 4 and onward, it just ruins any hope of getting the right signal. Meanwhile, since you as the player are allowed to pick any seed point, what your adversary's challenge is here is to spread the small amount of mass around in such a way that no matter what seed point you chose, eventually there's a sphere, generally not of the same radius, but eventually there's a sphere that has high probability of bad information. So say at this point, in the sphere of radius 1, we have this massive glob of bad information. And since the sphere of radius 1 is small, that ruins that seed point. And so the adversary's goal is to spread the limited amount of bad information in such a way that it will radially spread to any seed point and pile up there. But this says that it can't, because as the player, we pick the amount of bad information, the mass of the bad information low enough such that f here is the function describing the mass of bad information at a given vertex. This L2 norm will be small, which means this L2 norm will be uniformly small, right? So we can pick the same parameter for all the hypercubes, which is part of the problem. And that means, by Chebyshev, that there has to be some point, actually a lot of points, with small maximal function. So that means that the averages over all circles are pretty small. So what this did in practice was eliminate a bad research direction. So it did serve a practical result. But it didn't give a positive result. It just narrowed the search. On the other hand, I mentioned this partially because I think it's very believable, because the idea of signals emanating radially is a very natural one. This gives some idea that this could be useful in other contexts. So, and I forgot to follow through on what we're doing today. Later on in the same year, this was published in 2013, my colleague Ben Krause showed that for all p greater than 1, we have a dimension-free bound, and that well, the weak type endpoint fails, but I'm not going to mention weak 1,1 anymore because I realize that's a whole can of worms. But he showed that there is, depending on p, and it will explode as p goes to 1, a dimension-free bound. And then together with Alexandra and Ben, I joined, and we changed this to arbitrary cliques, where it will depend on the size of the clique, it will depend on p, but it won't depend on dimension. And so throughout the rest of the talk, we're going to think of the size of the base clique is fixed, and what we're kind of trying to deal with is dimension going off to infinity. Okay. Now, I'd already mentioned Stein's work. Stein looms very large in this, and the sort of framework for the whole theorem came from an old paper of his, I think from '61. And the theorem was, the paper's on the maximal ergodic theorem, so it's sort of a variant on ergodic theorems. If T is a self-adjoint Markov operator, and M is the maximal operator given by the largest power for a given x, the largest power of T, then we have a dimension-free, or not dimension-free, we have a universal LP bound. So I think this is kind of a remarkable result. And given that it is the framework for this, the theorems we're talking about today, we would wish that for all spherical averages, there's some corresponding index such that we have a pointwise bound of the form for non-negative functions. Pk of f is bounded up to a constant by some self-adjoint Markov operator, which, I mean, here we'll take the stochastic adjacency operator. So this is just a random walk, because this is kind of the canonical form here. It would be great if we could say that this spherical average is pointwise dominated by this. But unfortunately, it's not actually true. And it's not actually that hard to see why. So each of these operators is given by the expectation of f over a radial probability mass, radial with respect to x, that is. We can see what these probability masses are, how they act on the spheres. So keep in mind, by the way, since the clique power is vertex transitive, it doesn't actually matter that this delta is centered at x. All spheres are the same up to automorphism. I mean, all spheres of a given radius are the same up to automorphism. And so this is pretty simple. This is just a delta, right? This gives mass 1 to the sphere of radius k and mass 0 to all other spheres. What this guy will do...
Can you explain again what is this guy in the P1 KTL?
This?
Yeah.
So what I'm imagining here is just a random walk of some length. Okay. So here, k tilde is standing in for any length random walk, and I want to show that it's not going to be possible, I mean, show weakly that it's not going to be possible to find a length such that if we take a random walk of that length, that probability mass is going to dominate this one up to a constant. So maybe it'll be clear after I draw the next graph. If not, please ask. So we'll get something with some central limiting Gaussian-looking structure from a random walk. And it is possible, if big K is small enough, that we could actually pick a long enough random walk that this peaks at that sphere, right? That the expectation of this process is this radius. But even so, we're going to be capped at 1 over rad K mass to that sphere. Does that clarify what I'm getting at?
Yes.
OK, cool. Thank you. The point is, if you have a function with a lot of mass concentrated at the K-sphere, this will see that mass much more than this probability mass will. So this is hopeless, but we are inspired to compare averages. And it turns out that if we compare averages of these with something like averages of these, we can get such a domination. On the other hand, it's not clear why dominating Cesaro means, which I'll define in a second, of these spherical averages would tell us anything about the spherical averages. So we're going to come back to this, to these probabilistic bounds in a moment. But first, we're going to see how to split up the spherical averages in how to split up the spherical averages into a smoothed out part given by Cesaro means and a part that can be handled with spectral techniques. So for a fixed big K, if we take the Cesaro mean of the first big K spherical averages and look at the difference after the Abel summation formula and a little application of Cauchy-Schwarz. Cauchy-Schwarz in K, this is still a pointwise bound in X. X is fixed throughout this computation. But Cauchy-Schwarz in K, we get, this is equal to the sum from K equals 1 of, I'm writing it in this form so that you can see exactly how you would derive it using Cauchy-Schwarz, times the square function K equals 1 up to big K of rad K. This first factor is actually less than or equal to 1, not even up to a constant. And so the upshot of this is that we can bound for all big K. We can get the uniform bound that the spherical average is pointwise less than the Cesaro mean plus the square function, which is a pain to rewrite. In particular, we can get rid of the dependence on K on the right side. Right? If we supremize over big K here, we get, I'll define these in a second, the smooth maximal operator. And these are all non-negative summands, so there's no harm in sending big K up to big N, where we have the smooth maximal operator is simply the average of the Cesaro means.
Maximum.
Did I say average? Thank you. That would be the second Cesaro mean. Yes. The maximum of the Cesaro means up to big K. And this square function down here is this extended up to up to n. K equals 1. Now, at the moment, it might not, which might be an understatement. It's probably not evident why this is a useful way to break it up. Hopefully it will be by the end. But the motivation is that these smooth kernels are much easier to bound from this probabilistic standpoint. We will be able to do that in the way that this failed. Whereas these square functions play very nicely with L2, as square functions are wont to do. And we'll be able to use spectral methods there. And between them, we'll be able to get, taking a supremum over k, that the spherical maximal operator is bounded in L2, just extending this pointwise bound to an L2 bound by the smooth plus the square function. So let's put the square function off to the side right now. We'll come back to this at the end and finish up with the smooth maximal operator over here. Yeah, so I want to leave these up.
Do you have this k coefficient in the square function?
What about the k coefficient? Yeah, the k coefficient should be there.
Okay, because you didn't have it on this. On the left, you have an expression.
Yeah, it's square root of k squared. We got a k from the obel summation formula. We put half of it in the factor that disappeared and half of it here. By the way, if you want a reference on that, that whole thing is in the Stein maximal ergodic theorem paper. It's in Harrow, Kolla, and Schulman. They have reviews of a lot of this stuff. OK. Now, before we go any further, I just want to draw out the radial probability mass induced by these smooth kernels, which look pretty simple. It's just a uniform, but I want to just view this as on the order of 1 over k, since that's all I care about. It's just a uniform selection of the first big K spheres and then 0 after that. OK. This leads us to what I'd said earlier, that we would be sort of borrowing from Stein's techniques, if not black boxing his result. And so we start with the same seed bound that he does, which is a much older theorem of Hopf, Dunford, and Schwartz. Which says, if, I said this is a continuous version, there's a classical discrete version, and this follows just by looking at Riemann sums and limits. If we have a semigroup, is a semigroup of Markov operators so this means, if you're not familiar, just that the operator t plus s is equal to the operator t composed of the operator s. If you want, just think of this as a time evolution, right? If you freeze time after s seconds, start it and then freeze it after t seconds, that's no different than just letting it run for s plus t seconds. And that is sort of the intuition we have in our semigroup. So if we have a continuous semigroup of Markov operators, I didn't say continuous, this is trivial for us because all of our spaces are, I mean, they're getting larger, but they're all finite in and of themselves. So, but for soft reasons, continuous is unimportant. But I'll leave it up there. So if we have this family and we define the following maximal function. So this is time average. We have this maximal operator. Then, predictably, we have that an LP inequality. Sorry, depending on P for all P greater than 1. This could almost be viewed as a corollary of the Stein proof from earlier, except that these don't have to be self-adjoint. But that's dumb because that's like saying that you can build house lamps because you can build lasers. This is low tech used to prove that. That's why I bother to restate it. So our goal then is to compare this probability mass to a radial probability mass generated by something like this. And the way we do this is by introducing the noise semigroup. So I'm trying to think about what I should erase. I'll erase over here. So the noise semigroup, this is just on the clique, on the base graph, is computationally given by e to the negative t Laplacian with the convention that Laplacian is positive definite. I've seen both conventions, but more geometrically, intuitively, we can view this as a very natural process, a diffusion process, right? So if we look at K4, right, this is the mass that's induced by placing a delta at one of the vertices and then just letting it diffuse naturally. And it treats all of the other vertices equally because it's a clique. This won't be true if we look at other graphs. But in this case, it has a nice simple expression. And we're actually going to linearize it for, say, t less than small enough c. We can basically write this up to harmless constants as a convex combination of the this here being the spherical averaging operator on the clique, so stochastic adjacency if you like, linearizing at 0, we get we can use this as the noise operator. Keep in mind, by the way, that when we look at the smooth maximal operator, this is what we're trying to bound in LP now. It's good enough to do this up to Cn. The reason being that if we look at the max over k greater than or equal to Cn, we can just bound this crudely. Let's say look at p norm. This denominator takes care of everything. Right, is less than or equal to, well, here we have n plus 1. Here we have n plus 1 copies of something, of an LP contraction, and so it's, yeah. So there's no harm in just truncating our smooth maximal operator at a multiple of n. Past that, it becomes trivial. And that's why this linearization is really does no harm. So when we look at what our noise operator does, when we apply a noise operator to a clique power, we're just thinking of tensor powers of this operator, right? So if we're looking at, let's say, K3 to the 5, so we have 5 components. Each of them with a K3 in it. We start at a point X, which is some product, and then start the clock. As t increases, all we're doing is steadily moving the mass from here to here independently in each component. So in particular, this gives us an IID. The radius of the outcome is an IID, sum of IID variables. And this induces the following probability mass. So here we're going to say, for now, just fix little k less than or equal to big K. We're thinking about fixing a big K here. The only spheres that are seen by this probability mass are spheres with radius less than this big K marker. So, so those are the spheres I care about in my bound. So if T, this should be square root, is close to K over N, in the sense of being within square root of K over N, away from K over N, we get something like this. Something Gaussian looking that peaks and peaks close to K, so that K lies within up to a constant 1 standard deviation. And in particular, so this is rad K. In particular, this means that it gives probability on the order of 1 over rad K to that sphere. And the significance of this is that when we integrate, when we take a Cesaro mean, so we're going to take the time average up to K over N. Oh, sorry, not Cesaro mean, the time integral. We want to see what this does, what this probability distribution, so let's put a delta in here, what this probability distribution does to the sphere Sk for an arbitrary little k less than or equal to big K. And this is bigger than, we just restrict the integral to where it gives significant mass, right? Up to a constant, it gives full mass to the sphere of radius K, or maximum, not full. And so this will give mass 1 over rad K for a duration of rad K over N to the sphere we care about. And so up to a constant, this is at least 1 over big K. The upshot of this is that if we average these noise operators, we will have a probability mass that up to a constant dominates the smooth kernels. And in particular, we saw, right, we have the semigroup bound. I had said that the reparameterization was harmless. What I meant by that is that if we define our noise operator by, our noise maximal operator by the supremum over 0 less than tau less than or equal to c, these means of that this inherits the LP bounds.
Namely, this is like the opposite direction for it to go, because instead of concentrating, you're averaging over a bigger interval. You're averaging overall.
You mean instead of going to the more singular spherical?
Right.
We've already taken that leap. The reason that this is useful is that here we lose basically half a power of k when we average, whereas here we get back a power of k when we average here. And so in the long run, the smooth kernel is going to basically gain more by smoothing out than the noise operator. That might be a little too pithy, but this bounds the smooth operator. But now we still have to deal with this square function. And if you got lost in the last part, that's fine, because we're sort of starting over with the spectral portion. OK, OK, so we have our square function over there. And what remains to show is that it's bounded in L2. We'll actually square both sides by f. I'll put a question mark here. So let's take a look at these expressions. Well, this is the sum over x in the clique, k from 1 up to n. I might switch to a better marker now. Okay. Yeah. Rearranging the sum, this is sort of the whole point of square functions, we can bring an L2 norm all the way in here, and what we get is the sum over k of the L2 norm squared of this difference. If you're not used to this computation, it's pretty quick. But the point is, these spherical averages on the clique power are self-adjoint and they commute. If you don't believe me, we'll see why in a moment. But they do, so they can be simultaneously and orthonormally diagonalized. Jeez. Yeah. Be an orthonormal eigenbasis for the spherical averaging operator family. Then we can write this L2 norm as the sum over all eigenfunctions in this basis of, I'll explain this expression in a moment. Although you will likely figure it out from context. So I'm borrowing some notation from Fourier analysis. This really is discrete Fourier analysis. By this, I mean the eigenvalue of this function associated with the kth averaging operator. Here, I mean the inner product between the function f and the function v. Oh, sorry, there's a k here. And the upshot is that I can bound this by sum over k of the sup, or max, I guess, over v, of these eigenvalues. Squared times the 2 norm of f squared. Right? This is an orthonormal basis, so this sum comes out to the 2 norm squared, and I'm just pulling out the largest of these coefficients. And so all of a sudden, we've gotten rid of f, and now this is just a question about the spherical averaging operators and their spectral properties. Right? So now we're going to have to say more about, about the eigenvalues and eigenvectors, but we've gotten it to a nicer form, I would say. Notice, because of the structure of the clique, really because the clique has diameter 1, that there's a very nice relationship between averaging operators on the clique powers and on the underlying clique, which is that averaging over the k-sphere on the clique power is the same as just picking uniformly randomly a k subset of the n components and taking your and applying the operator that's the stochastic adjacency on the clique and all of those bad components, and then the identity everywhere else. Right? So pk of delta is just pick k components and change those and only those. And these eigenvectors here are just tensor products of eigenvectors of the adjacency, the stochastic adjacency here of the clique. Simply because, I mean, these are convex combinations based on this observation of tensor products of the clique adjacency and the identity. So certainly we can orthonormally diagonalize that by this. And what we get is up to a normalizing factor, B, our basis is the space of functions of this form. Y is in K M N. What I mean by this is C here is a primitive mth root of unity, and we identify vertices with a numerical label 0 through m. This is just more for ease of notation than anything else. And then this is just a numerical dot product out. But these are the tensor products of eigenvectors. And what we see is that the more of the components of a given y that are not 0, right, the more components that are not the constant eigenvector. So we see C, y, x, this is on the clique, has eigenvalue 1 if y equals 0, right, then it's just the constant vector, and this is a Markov operator, and negative 1 over m otherwise. This is a pretty straightforward computation. So what we see is that the eigenvector, the eigenvalues here are given by the probability that if you take a random component in the spherical averaging operator, and that operator is the adjacency rather than the identity on the clique, and then you take a random component in this eigenvector, and that is an oscillating vector, not the constant, that probability determines the eigenvector, because if and only if there's a collision do you get a non-1 eigenvalue. And this plays into some massive sum, but the two observations to be had here are, first of all, if V has a very low frequency, right, that is, V has very few oscillating components, then these are going to be very similar. They're not going to be small, they'll be close to 1, but they will be close to one another. If V is, all ones with one oscillating component, the probability, the difference in probability here of a decay is just 1 over n, right? Because it's the difference in probability that the first component here and the first component here are the adjacency rather than the identity. So as a result, this gives us, with a grain of salt, that if V has R non-constant components, then the difference is equal to, with some shifts of indices, but for all intents and purposes, equal to R over n times pk. Right, so the lower the frequency, the more gain we get from that difference. And if k is bigger, if the product of k and the frequency is large, that means a high probability of collision, which means a high probability of cancellation in the case of the hypercube, or contraction of by powers of m in the case of higher cliques. We have that this thing is bounded by e to the negative omega rk over n, where this corresponds to the probability, in some sense, of a collision of an adjacency in this operator and an oscillating component in the eigenvector. And so as a result, this thing has to be smaller than, I guess I should put quotes around here too if I put an equals, has to be smaller than k times r over n e to the negative rk over n, and basic summation tricks give you that this is bounded up to a constant by 1. If you like, I mean, think about this as an integral in k and integrate by parts. And that does it. That bounds this thing in L2. So, I mean, a lot of steps, but...
So how does the bound depend on the size of the clique?
How does the bound depend on the size of the clique? The linearization process shouldn't care much, because as the clique gets larger, it just gets more and more like a diagonal. Larger m means quicker decay. I'm not sure, is the short answer, but I've been so busy trying to actually get the dimension-free bounds for other graphs that I haven't thought much about the actual constants within a class of graphs. It's an interesting question, and at some point I'll probably go back through and check.
Right, and you get matching lower bounds from specific functions.
You get matching lower bounds.
Do you find the right rate of dependence, as the clique grows?
Yeah.
Do these constants depend on the clique size? So from the argument and, are there matching lower bounds?
I can't remember off the top of my head, but I can get back to you. Yeah, that's the basic proof. I'm a little over time, but I'll just say where the project is going, because I may as well. So my main thing now is trying to figure out to what class of graphs this phenomenon extends and for what class it fails. For instance, for powers of trees, we have exponentially bad bounds. It's not that hard to see. I have a proof on my website, at my UCLA website, if you'd like. The LP bounds of the operator grow exponentially in dimension for trees.
So it's not just the bounds, but the maximal function themselves. The functions themselves were. This is the bounds are bad, but the truth is bad.
Sorry, say that again?
It's not just that the bounds you can prove are bad, but the actual behavior is bad.
Yes. Yeah. The point is that if you take very large radius spheres in a tree, it really only sees leaves. So if you just put mass on powers of leaves, then any point sees that mass. But I don't want to go into more detail for time reasons. So the main result I have now is that the 5-cycle graph has L2 bounds for its ball maximal operator, which is a far cry from what I really want, but it deals with a lot of the main issues caused by the clique having this nice property of a simple relationship between averaging on the clique powers and averaging on the clique. So I'm optimistic that will move forward and we'll be able to get small p. Yuval had a nice suggestion for a reference that was an improvement on Stein's original paper that this was sort of following, to maybe get small p's through simpler means and to get explicit bounds in p, which would be nice. But that's where it's going, and I'm hoping that I can prove eventually that at least for Cayley graphs of abelian groups, you can get dimension-free bounds. And then if that's true, try to expand it as far as I can and see where it stops. So, thank you very much.
So what's your guess on what's the right condition on a graph? What?
At the moment, so it's the techniques clearly require, the spectral techniques anyway, clearly require that the spherical averaging operators in the base graph commute with one another, because that's the necessary and sufficient condition for them to commute in the graph powers. And I think there is a decent chance that is sufficient for dimension-free bounds, but that's definitely not obvious.
So that's true in that you need a billion. Right? So what is the assumption? So if I'm in a Cayley graph, what is?
Cayley graph of an abelian group will have that property.
Right, but if it's not a billion, then
it may or may not. It depends on if it can be, constructed otherwise. It would include distance regular. It would include Cayley graphs of abelian, and I'm trying to get a sense for, in the process, what that condition means geometrically. I have some guesses at that, but those are things that I don't want to say because I haven't explored it enough, and they might be stupid guesses.
This is in terms of technique, but say if I'm if the base graph is any transitive graph,
Yeah.
then you have a counterexample needed. Sorry. So the trees, they have these very different, leaves are so different from the center, but if you have a transitive graph where all vertices look the same, should that be enough?
Yeah, it's a good question.
I mean, won't pk and pk minus 1 commute in this case? If it's vertex transitive?
It's possible, but I don't think that's obvious. I mean, I don't think it's obvious for non-abelian groups, which are a special case of that. But
That's not true.
yeah, so it might be it's an odd condition right now. It looks very algebraic and contrived. I'm hoping that there's a more natural way to phrase that condition, but at the moment, my main focus is getting this 5-cycle bound and moving towards, because I think it'll also become easier to characterize when I have a better sense of the proofs for wider classes of graphs.
Okay.
Thank you very much.
Any other questions?
Just maybe p, I mean, you only showed p equals 2.
Yeah, I meant to say this partway through. I decided to only show p equals 2 because this is something you've all had alluded to. The proof for p less than 2 uses techniques that are totally different and very technical. It's interpolation theory, and most of the juicy stuff is in the L2 bound. So, you know, it's possible that I'll be able to present on the LP bounds if Yuval's suggestion pans out, but at the moment it's just not worth the time because it's pages of stuff. There's a good reference in Nevo and Stein's paper and in the Stein Maximal ergodic theory paper. That came from.
So Stein himself also first starts with 2 and then...
Right.
That's okay.
I mean, the proof does start, this is the beginning of the proof, but then the rest, so it's a convenient stopping point, but the rest of it is just like very arithmetic and complex analysis-y, so.
All right, is there no more questions?
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.